We're asked if this function is a one-to-one function, so let's graph it. It has a y-intercept at 3, and it has a slope of up 1 and over 1, so it looks about like this. It is a function because it passes the vertical line test, which is, if you draw any vertical line whatsoever at all, it never touches this function in more than one point. If this function f also passes the horizontal line test, then it's a one-to-one function. If you draw any horizontal line through there, you see that it can only hit it most at one place. And so horizontal line test is passed, vertical line test is passed. This function is one-to-one. Note, unless you have a horizontal or vertical line, any other kind of line, whatever line it is going to be a one-to-one function because it always passes the vertical and horizontal line test. Now, if a function's one-to-one, then it has an inverse, and so let's find the inverse of the function. The way to do that is to follow our steps. So we replace the function notation with a y temporarily. Then we switch x with y and y with x. So everywhere we see a y, we put an x. Everywhere we see an x, we put a y. And then we solve for y. I'm going to subtract 3 from both sides and then turn it around. And then we take our y, which we originally had replaced f of x with y, and we replace y with the inverse notation. All that fancy notation means is it's just a special kind of function, a special name. It could be I of x for inverse x, but it's just the inverse of f of x. It doesn't mean the reciprocal. It doesn't mean a -1 power. It's just the inverse. So the inverse of this function is this one. And we know something about inverses. If this is the graph of our original function, something like this, and this is the graph of our inverse function, something like this, we know that if we graph a function and its inverse, here's the function, here's its inverse, that there should be symmetry around the y equals x line. Well, where is the y equals x line? The y equals x line is right here. And do you see that there's symmetry around the y equals x line? That's important to know. Let's see what Desmos has to say, if anything. So here's our original function. Here's the inverse function. I had to call it I for inverse instead of f, sort of to the -1 power looking symbol. And notice that there's symmetry around the line y equals x. And so that's exactly what we expected. This is a line. The y-intercept is 0. The slope is 2, so it's a little bit steep, but it's certainly not horizontal or vertical, so it's one-to-one. This is going to have an inverse. We're going to do our steps. Which are replace f of x with y, interchange x and y, divide both sides by 2 to get y by itself, and then use the inverse notation in place of y. So we have that the inverse function is x over 2. Now where is x over 2? Well, it has a y-intercept of 0, but it has a slope of up 1, right 2, so it goes like this. And notice there's symmetry about this line. Y equals x, we can always expect that symmetry. That's a good thing. Let's go see what Desmos has to say about this. Here's our function. We see it has a y-intercept of 0, it has a slope of 2, it's a linear function, it's one-to-one, so it has an inverse. Here's our inverse function, much as we thought based on our rough sketch in our work. And then here's y equals x. It's symmetric about y equals x because we found the inverse by interchanging y and x. And if you think about that a while, it's possible. It might make a little bit of sense. We'll talk more about it later. Here's our function. It's a line. The y-intercept is at 0, -10. I've declared this to go by 5, so this is -10. And the slope is -1, down 1, right 1, so it looks kind of like this. And it's going to have an inverse because it's 1 to 1. And so let's find the inverse. Place the function notation with y, interchange x and y. Solve for y. I'm going to add y to both sides. I'm going to subtract x from both sides. And I have y equals minus x minus 10. And I'm going to put in the function notation for the inverse. And now I have kind of a strange situation because the inverse of this function seems to be this function, and that could mess us up a little bit. But notice these two are symmetric with respect to the line y equals x, and so it's possible that we're correct. Let's see what Decimals has to say about this situation. You can see that the inverse of f of x is, in fact, itself, and there is symmetry with respect to the line y equals x. This is still a little weird, so I want to show you that if you do a composition of functions, if you take the function h, and instead of putting x inside it, you put the inverse function inside it. That's a composition of functions. It's what it's called. Can we show that this is x? Because if these are in fact inverses, this will always need to be x. So let's try it and see what happens. Inside of h, we're going to put this. And that means that we're going to take h, this is h, and we're going to put this inside of it. So we're taking h and we're putting the inverse inside of it in place of x. And we're going to do the distributive property carefully. We get a plus x and a plus 10. And these cancel each other, and we get x. Not only does this have to be true when you have inverse functions, but it has to be true the other way around. So if you take the inverse function and put the function itself inside, it has to equal x as well. So I'm going to take the inverse function, that's this one, and I'm going to put this one inside of it. And we get 10 plus x minus 10, which equals x. And so there's algebraic proof that these two are in fact inverses of each other, even though they're the same function. It's kind of weird. This is a line. It's not vertical or horizontal, so it is 1 to 1. It passes the vertical line test and the horizontal line test. To find its inverse, we do these steps. We interchange the x and y. I'm going to subtract 4 from both sides. I'm trying to solve for y. I'm going to multiply both sides by 3/2. I'm going to distribute because I'm aiming for the equation of a line that's pretty easy to graph. this would be minus 6. And so I now have the function's inverse written this way. The book says to graph them, and I'm going to, but I want to do that composition of functions because the composition of a function and its inverse should always be x. And so I'm going to take f and I'm going to put in its inverse. What does that look like? Well, I'm going to take the function f. There it is. I'm making room so I can, instead of an x, I can put its inverse. And the value of this is you can see how this function and its inverse are kind of undoing each other. When we distribute the 2/3 through, we get x, and we get 2/3 times negative 6, which is minus 4. The 4's cancel, and sure enough, this is x. If we want to go the other direction, we take the inverse function down here. And we put this function inside of it. We distribute, we get x, we get 3/2 times 4, which is 6. And do you see that when we do the composition of a function and its inverse in either direction, they're undoing each other and we get back to x, the thing we started with. And that is the hallmark of inverse functions. They undo each other's effect. So if you take an x value and put it in to a function and get an output, the inverse function will take that output and get you back to x. And that's what we're finding here. It did say to graph this, so let's go to Desmos and graph our results. So we have our original function. You can see its y-intercept is 4, and it's going up 2 and right 3, up 2 and right 3. We graph our inverse line, and it looks, if we go down here, we can see that it has a y-intercept at negative 6, and it's going up 3 and over 2. And we know that there ought to be symmetry about the line y equals x, and notice there is symmetry about the line y equals x. And so, again, we've learned quite a bit about functions and their inverses.